Okay, so generally we use Naragami distribution fading for our for analysis purposes. So when you have Naragami fading, the fading power actually looks like a gamma variable, right? And it can have different parameters from line of sight and non-line of sight, right? But we also saw in general when we have worked on many papers, and we saw that exact fading distribution doesn't have much impact. Okay, for example, in the inside perspective, of course, it will change your normal exact answer, right? If you want to compute what is the exact coverage performance, it will change. But if you just want to look at the insights, it is not very much impacted by the distribution you are talking about. So we also validated in many work that even if you take Rayleigh distribution, which is very simple and it gives highly tractable results, it also provides you very good insights. Again, those need to be validated little bit later on with the actual fading distribution. So that is why you will also find many millimeter wave work which just take the Rayleigh distribution instead of Naragami. Because Naragami makes things very complicated. I mean, not very complicated, but there is some difficulty involved in that. Okay. So now let's come out to the association law. We assume the maximized average receive power, and since we said that the line of sight base station and non-line of sight base station has different path losses, this means the average power, maximum receive power is not equal to the minimum distance criteria, right? If you have single types of base station which has same path loss, then if you want to have maximum receive power, you just connect to the closest base station, okay? But this is not case here because non-line of sight base station can be very close, but still they have less power, so you do not want to connect with them. So you actually have to look at the average receive power, okay? And this is excluding fading because you want to average, and without the antenna gain, because you can always point the antenna gain into that direction, okay? So receive power, what we say is mixture is a multiplication of power, some fading, path loss, and antenna gain, okay? Now this antenna gain depends on the angle of the user from the interference. So for example, this is user, this is the interference beam, interferer, and it's pointing in this direction. So you want to see what this angle is, and based on this angle, you will decide what is the directivity gain of this base station to this user, okay? So there's many base stations and each base station is pointing to its own direction, so you can model this angles as randomly oriented between 0 to 2 pi, okay?
Actually, your HG and L, they are not deterministic, they have a distribution.
Yes, which one? HJ, na?
HJ, what is HJ?
HJ, right?
Yes.
This is fading. This is fading. So we are not considering this in the association.
No. Is a power coefficient HJ?
Yeah.
Distribution will be different.
Gamma distribution. His distribution is gamma distribution.
The gamma is a distribution when we talk about envelope, and when we talk about power, distribution is not same. You are giving the expression power. Power, HJ, not be an envelope distribution, it's a power. Then in that case, the distribution will be different. This is number point 1. The second point is it has a distribution. How then we can write Pj, because it has to be integrated over the power.
Yes, so we do that.
Pi,
so we
Pj is a power, it's average power. And the average has to be taken over the distributions of the random.
We do that. So when we talk about assigner, that's instantaneous, depending on the current received power. But when then
this is instantaneous power.
Yes, but so when we talk about this average power, we do not consider fading. We only say that you have transmit power, you have path loss. Only based on these two, you want to associate to the base station. But we have line of sight and non-line of sight. It means the power is not dependent on the distance in a different way. So you just don't consider the closest one. You So you find the closest in line of sight, you find the closest in non-line of sight, and compare the two and connect to that one. Once you do that, then you talk about instantaneous assignment. There you have to consider a distribution that you have many random variables, even the look.
Clear. Mathematically it is not clear. When you have written the ratio, sigma square is the noise power. Each of the terms will be power. When it is power, then again you can't say it is instantaneous.
Noise is generally considered in all system level simulations. System work.
Is it instantaneous?
SINR is
or it is an average SINR?
SINR is instantaneous at any moment, but even then noise is generally taken as power.
What is your average SINR?
You compute the expectation of this.
Okay.
So with respect to many Hj is also random, antenna gain is also random, and the interference has multiple summation over different fadings, different locations, and different antenna gains. So there are many random variables here.
Yes.
So you have to compute distribution over everyone.
Yes.
Okay. So that is I am just trying to explain one by one that this theta is the angle between interfering at the user, right? For each one we can assume that this is randomly because it is serving its own user. Okay. So you can see that this angle for this user it may look random to you because he doesn't know where this beam is actually, this user it is serving. Okay. Okay, and then for the rate part, once you get this average rate, then you can also compare with average with instantaneous rate. Sorry, when we have this instantaneous SINR, we also compare it with relate with instantaneous rate. Okay, again, so I've gone a lot of practical implications with it, but if we talk about the upper bound, we mainly see that the expression we can write in log 1 plus SINR divided by the resource for each user. So suppose you have total bank WK and then you have NK blocks, means each base station has NK users. So it has to divide its spectrum into NK different blocks. Suppose you assume OFDM kind of block this thing. So when you divide these blocks into different frequency, each user get WK by NK. Okay. NK is the total number of users per base station, and you have total bandwidth WK, so per user is WK NK. And what is the NK? NK is total number of users per base station, and again we have to compute a distribution, right? So the users are located in a Poisson point process, and base station are also located. You want to find when you divide the cells between base station, you want to compute how many base stations are there in each, how many users are there in each base station. Okay, and that is on the average, this is given by this formula, 1 plus 1.28 lambda u AK by lambda k. Lambda u is the user density, lambda k is the base station density, and multiplied by the association probability. Here you have only one here, so you have association probability 1. So, but the key point is, people will say that average load over each base station will be lambda u by lambda k. Suppose you have lambda u density of user and lambda k density of base station, then the average base station will have lambda u by lambda k, right? But here we say the answer is actually 1 plus 1.28 multiplied by lambda u lambda k. This is coming from the fact that the base station you are looking at is actually connected to the receiver at the origin. When you condition on the fact that you are choosing a base station which is where the user is connected to it, and you want to look at the distribution number of users connected to that base station, there is a bias to it, right? This is same as when I ask you, if you go to a grocery market and try to find, there are 5 lines, and you want to compute the average length of all 5 lines, there will be some number. But when I say that pick a random user and then ask what is the queue length he sees, right? This will be different because when you select an average user, there is a high probability that you will select from the line who is bigger because you are selecting an average user, right? So you see a is a more large delay than when you just look at each line individually and average out its delay. Same as here, when there is a base station is large, when the base station area is large, you have more users into it, right? And they get less and less data rate because there are more users into it, okay? So when you put this bias factor into that, there is a higher probability a user will be in a large base station cell. You get a worse performance than just looking at each base station cell's individual performance. So that is why this is coming. It's actually part of Feller's paradox. This expression comes from that. So you have to make sure that the distribution of the tagged base station means the base station you connect to is different than the distribution of a random user which you do not condition anything on it. Actually, yeah, there should not be any case mistake. So 1.28 lambda u by just lambda, sorry. Forget about any k, 1.2 lambda u by lambda, just that. Okay. Then second thing part is partial load modeling. So we saw that, in millimeter wave, you will have dense deployment. Many of the base stations may be switched off at a point. Okay. But we always assume that all the base stations are just transmitting all the time, they are full buffer, right? Which will not be the case with millimeter wave. So we have to make sure that we model such kind of partial load that we find which base station doesn't have any user and we can switch it off, right? So when you switch it off, the active transmitter is again a thinned version of the original one and will still be a PPP, but the density will be smaller, so you get less interference. So how do I compute it? This result is there that number of users associated with a base station I think just forget this M. This is for multi network. Just forget this M is there. So number of users associated with any base station is given by this distribution. The key factor is that N is given by ratio of base station density, user density and base station density. So you compute N, which is user by base station density, and you compute, this is a distribution of number of users in any cell. Okay, that is different than this distribution. This is the distribution given to the tagged base station, the base station you have connected to, right? This is the base station, any random base station which you connect to, which is not conditioned. So it may be smaller or bigger. So this distribution is there, and from this you can compute what is the probability that there is no user associated with it, right? And if there is no user associated with it, you just turn it off. So this probability you compute equal to 0, you compute the probability, the base station is switched off, and then you multiply that probability with the density, you get the density of the active users which are actually on. Okay. Yeah. So, partial, of course you can put more complicated file FTP models or something like that, but that will be difficult to analyze. So we take a little bit approximation from that. We still assume that the files are coming at each base station, right? So you get a lot of users associated with it, and then you try to find what is the probability that any base station, if one base station doesn't have any traffic or any user into it, right? And that we can compute just by the yes. No, when the user will come, the base station will turn on. So they keep track of those things. So there is some kind of mechanism there in a dense network that if you do not see any user, you switch off, but you keep on still actively searching for it. Right? And this is true for many dense network. When you have more Wi-Fi's than users, then many of the Wi-Fi just switches off in regular case. So this can be actually seen as per bandwidth slot also. Suppose I am looking at a user and is assigned some chunk of the bandwidth, right? So I am mainly concerned about how many base stations are actually in that chunk. Okay, that is more relevant question, right? So all this density which you are actually looking at is actually telling that. So what I see that there is no user for that base station in that chunk, so it will switch off operation for that. So this is the same as saying that this base station is switched off. So the user density I am talking about can also be seen, the user density for that particular band. Because the user distribution is again random. So you deploy the users according to a Poisson point process. So each cell get a different number, even if you take two base stations of the same size, they have different number of users into it, right? So it is not looking at because one of the cell, the base station are Poissonly located, but each cell, the area of the cell is not Poisson distributed. You want to compute how many users are there in each cell. So users are Poisson distributed, but the area itself is again random for each cell, and that is not Poisson distribution. But if you compute the mean of this, the mean of M is come out to be n. On the average, there is n by lambda u by lambda users per base station. Okay, so once we have this modeling thing, when I'll just give a simple example of how we are using for millimeter wave. Okay, first of all, so we assume that we connect with the user which has the highest receive power. Okay, just assume I connected to line of sight for this case. So, and I call them 0. I call that user x0, index it by 0. You can index in any terms. So suppose this is my user, this is my base station connected to it. It's at distance r0, 0 because I just call the base station I index to by selected is as 0. Okay. Now you take any other base station and its distance is rj. Okay. So the condition is that the power from the serving base station is greater than any other base station which can be in the phi, right, which is point process. So line of sight, this will reflect this condition that both are, so this is line of sight I assume. If j is also line of sight, then both have similar kind of terms. This will basically result that rj should be greater than r0. If both are line of sight condition, line of sight base station, then this just means that rj should be greater than r0. r0 should be the closest base station in line of sight. Okay. So this means there cannot be any base station in this area. There cannot be any line of sight base station in this area. Okay. Similarly, for long line of sight, this expression little bit changed because instead of CL and alpha L, you have Cn and alpha N, which reflects the gain and the path wave exponent for long line of sight. And in this case, you get that rj should be greater than a function of r0, which we call dr0. So there cannot be any non-line of sight base station less than in the ball which has this radius around the origin. Okay. So in both cases, the value is different, but in both cases you have a region around the user where the interference base station cannot be. Because if the base station is there, you would actually connect to that instead of connecting to the R0. Okay. So this creates an exclusion zone around the receiver, and the interferer can only be outside that region, which was not the case with the ad hoc example we saw, because the receiver transmitter pair were already decided, so the interferer can be anywhere. Where here the interferer can only be away from the one who you connected to. That is because of the cellular, how cellular systems work. Okay. So now we have to talk about what is the probability that base station is connected with you. No, because you can always steer your beam into the direction of the user, right? So no matter what base station I select, the base station will steer for me in the end. So right now whatever the antenna location it doesn't matter there. You have to assume that whenever I connect, he will always put his best gain to you. They all have the maximum gain same. Okay. So distribution of the, suppose I'm just doing for line of sight base station, but the analysis is exactly same if you connect to non-line of sight base station also, right? So suppose I connect to the line of sight base station, index 0. First of all, I want to see what is the distribution. So this is of course the closest base station in the line of sight, right? That is why it is getting connected. So what is the distribution of the closest base station in line of sight? That is given by this term. This you can see so how do I compute it? The density of the line of sight base station is lambda into P line of sight. That we covered, right? Density of the line of sight base station is lambda multiplied by the thinning probability, which is line of sight probability. Okay. So probability that there is no base station less than R is given by e to power minus lambda R, lambda into area pi r square. Okay, but this is non-homogeneous. So instead of lambda pi r square, you have to do lambda x dx. Okay, there this term will come, lambda p s dz. Okay, and then you differentiate this term to get the distribution. Okay, because that is the probability that you have a closed base station in R. And then similarly, this is also there, and then along with the condition, it is connected to the line of sight base station, means there is also no line of sight base station within the closer than dr. Right, dr is this term. So this is of course line of sight base station, the closest one. Second, the base station, there is no line of sight base station also closer than dr. Then only this base station will be selected. And similarly, that probability will be given by this thing. So exponential minus lambda pi, this thing. So that is same expression which we covered in the last part, that lambda pi r square, but since lambda is not homogeneous, you get lambda x dx. This is nothing but lambda x dx, because lambda x here is lambda multiplied by non-linear probability, and then you do dx, but of course this is polar coordinates, so you get g dz in 2 dimensions. Okay. So that overall probability that the serving base station is line of sight and its distance is given by this probability multiplied by this one. Again, this is, I did not do a rigorous one, but the key idea is that you actually condition on the fact that you connect to the line of sight base station. So you get 1 upon association condition probability also, that you connect to the line of sight, right? Then depend on that you compute the probability, which comes out to be actually equal to the integration of this into this. And then you differentiate to get that. So both are actually distribution instances, you are computing the distribution of this one. But one acts as a conditioned probability or something. So there is a rigorous proof of it. I just covered something for this class. Yeah. Similarly, when I talk about interference distribution, the same thing is coming here. You have association law because of that. No interferer can be inside that region. Okay. So all the interfering base station will be outside R0, and all the interfering non-line side base station will be outside dr0. Okay. So this will be helpful when we compute the Laplace function of the interference. Okay. Before going that, we do one approximation here. Since we assume Nagami fading, the gamma distribution of fading, we cannot actually evaluate the exact ones. But there is a tight upper bound given by which algebra lemma, which says that probability h is greater than gamma, where h is a gamma distribution with new parameter, is given by this expression. Okay. And when V is 1, this just become Rayleigh fading with, so h become exponential, and then this is actually equal. So that is exactly equal to V by this one, e to power minus n lambda. Okay. So basically I just have e to power minus gamma here with some parameters, right? So these are all exponential terms. The key point is that as you see in the also in the example we did, if you have distribution in the exponential form, it is easy because the whole expressions become the whole SIR coverage expression becomes into a exponential Laplace term. Okay. If you do not have this exponential, it becomes very hard to compute. Okay. So let us see how I can do it. Assigner coverage at line of sight base station I am only considering for now. Suppose I call it PCL. The probability the assigner is greater than T. This is again we are only taking the case when we have line of sight base station. So the probability assigner has H0 multiplied by the antenna gain multiplied by the line of sight gain and path loss. We just this should be minus alpha L. So instead of assigner, I can replace all term from here to this side. This become H0, which is the fading from the serving base station to the user, greater than T n plus I. This is noise plus interference divided by antenna gain G1, because I assume the user the base station can always T to the user. CL, which is line of sight, and R0 alpha, this should be minus alpha. This is the path loss. Okay. Which is just coming from the serving power, I transferred this here. Now H0 is a gamma random variable. From using the previous this lemma, this is similar form, H greater than gamma. I can write this in this, before that we can, this R0 again is the distribution of the serving base station, right? R0 is the distance from the base station to the serving one, and again that is given. So there you have to also compute this expectation with respect to the serving base station distribution. Okay. So you integrate this term with respect to the serving base station distribution we just computed. Okay. Then this term has a H0 into it, and using the Alger lemma, you can just write this term as a summation over n to 1 nu, and here this term, this gamma just comes into exponential. So this becomes exponential minus n eta Tn plus I, G1 here R0 minus alpha distribution of this. Okay. Now you can take this summation outside integration. This expectation is with respect to interference because all other parameters are now averaged out already. Interference, so when you write this, you take this summation out inside, and from this expression you can again take the noise out, because noise we assume there is a fixed power here. So the noise is outside. Only term here in expectation becomes this, which is expectation with respect to interference. Now if you look at this expression, this is interference multiplied by some constant term. Okay. This is again nothing but the Laplace functional of the interference. Okay. This is the interference multiplied by some constant terms. Okay. So this is nothing but the Laplace function of the interference. Okay. So you got summation over integration. This is noise term. This is Laplace function of the interference averaged over the serving base station distribution. Okay.
Left hand side.
Yeah, so if it comes here, it should be dividedness, it should come out. If it goes to the upside, then there will be R0 alpha. If it's coming inside, it will be R0 minus alpha. Do you have a chalk here? So you have this greater than T by I plus N. Okay. So you take this I plus N, it goes here. This whole term comes below. No, this is signal. This is signal power. So what is remaining is to compute is the interference of Laplace functional, right? And that is similar to one we did in the random ad hoc case. So here the interference is again is a summation of the interference of line of sight and non-line of sight. Again, each one is an independent PPP because they are both thin version. So you can separate them out into two different parts. Laplace function of the interference on the LOS base station and the interference from the non-line of sight base station. Okay. So let's take it the first part. This interference from the line of sight base station is given by this term. Again, this is similar to what we did earlier. This is the PG. This comes from the PGFL of it, or the Laplace functional. Both you can see, and then if you apply the same Laplace functional here, you get 2 pi lambda 1 minus e to power minus fx was there, and then multiply by density of the base station. Now the density of the line of sight base station is lambda multiplied by the PLOS, not just lambda. Okay. Again, the fading we still have it here, so we have to still average it out with respect to fading. In the previous case we had exponential. So for exponential this is 1 upon 1 plus this. For gamma fading, again this is nothing but the moment generating function of the gamma variable, but also there is some G. This is antenna gain. Again, antenna gain is random here because it can be, if you are aligned then it will be full, you get G1. If you are not aligned then you will get G2, right? So you can compute this term. The expectation is for G, antenna gain and fading. Okay. So again this is just two terms, Bernoulli random variable with two G1 and G2 value. For G1 with this probability of hitting aligned beam, non-aligned beam, and so this is aligned with this probability multiplied by G0 is the antenna gain, G1 is the antenna gain which is not aligned, right? It comes to the side lobe of it. Okay. Now this is just EH, e to power minus this term. I miss H here. There should be H here. SH, it should be SH and SH here. And this is H multiplied by some constant. This is same as the moment generating function of fading, H with the gamma, which is actually given by this. Okay. So e to power minus H multiplied by S. Expectation with respect to H is 1 upon 1 plus S to power nu. Okay. So this term. Similarly, you can also get this term. This is 0 here, this is G1 here. Just summation of the two. If you can put this back here and you get the complete expression of the Laplace transformation. The interesting thing is the integration is only going from R0 to infinity. In ad hoc case, it is going from 0 to infinity. In this case, it's going from R0 to infinity because interference will always be outside the ball of R0. So if they are everywhere, then this will be 0 to infinity. But there can be only outside R0, so this is like that. And similarly, you can do for the second part, same expression you can get, right? Only thing the parameter will be non-line side because the interference is from non-line side base station. The density is also non-line side and the integration is from dr0 to infinity because non-line side base station will be away from dr0 distance. Okay. Once you compute this, you put it back into this expression of Laplace, right? You get the probability of coverage that when you are connected to the line of sight base station. Similarly, you can compute when you are connected to a non-line of sight base station, what is the probability of coverage. If you add the two, you will get the total probability of coverage you will get when you are connected to any base station. Okay. If you just take Rayleigh approximation, you can put nu equal to 1. In that case, the whole result is not an upper bound, it is actually exact work because Azuma lemma is true if you have nu equal to 1. It's not just the bound. Okay. So this is some simple one basic example of millimeter wave. But when you talk about different kind of other examples, suppose you want to include partial buffer into it, or you want to talk about superposition of different operators, you want to have correlated blocking. All those things we have discussed in this tutorial. You can always mix them with this analysis, and it's not very difficult to do. The steps are very similar. Right? Steps will always be this, and then you can just add. Suppose you have two networks. So instead of this probability of coverage, you will have 4 terms connected, and you have to compute the association probability that you are connected to each one of them. Okay? In the same way we have connected here with line of sight and non-line of sight base station. You can also talk about when you have closed access. You have 2 networks, but you can only connect to one network, but you get interference from all other base stations. So that is also you can do. Okay. So in all this expression, the idea is first write SIR coverage expression, right? Then first solve for distribution of serving base station. Then second is remove the conditioning of the fading variable from the serving base station. And you should hope to get a Laplace functional or the derivative of Laplace function in worst case. Then you compute a Laplace function of interference, okay, using the Laplace functional of the PPP, and you just put it back and you get the expression. Okay, same thing, exact thing we also did for the random ad hoc case also. Okay, only difference in cellular is that you do integration only from R0 to infinity rather than doing from 0 to infinity. Okay, any question until that? Okay, so it's a little bit heavy for analysis, but these steps are very standard, and once you get a hang of it, you will see that all the other expressions are kind of similar to it, right? And this is one of the type we actually handling HEPNet, because you are actually having 2 types of network, line of sight base station and non-line of sight base station. You are computing the association probability to each of them. You can connect to any of them, right? And you are getting interference from both of them. So it's a type of heterogeneous network.
In all of this analysis, if I understand, qualities
So this is not the exact, because we already did this Alzheimer lemma we put in the starting place itself.
I mean the computation of the probability.
Yes, this is there. But if there is other works also, like you can either use, there is a Fardy-Bruno lemma, we have done it in another paper, where you can write in an exact term, but you have to use the derivative of the Laplace functional. Okay, so gamma function can be represented as summation of the terms, which includes Laplace functional. Here it only had exponential terms, so that was little easy to do. But that was also is not that difficult. So you could, there you get exact expression. There is other some other way where people use Gill-Perez lemma also. So avoid computing explicitly this. Or Rayleigh approximation people also do. One other paper I had this and found the insights kind of similar for both of them. But again, now Rayleigh fading is very easy, but Nagai fading there is some kind of approximation or some complexity is there. So you have to make a call on your side.
That model wants to develop.
Yes.
The question now is whatever analysis that we have done, we have made a lot of suggestions regarding model. Who owns the model is some experiment not done. I think not be a very useful model for the result.
So the experimental,
That verification
yes.
is being made.
So this
That the Rayleigh distribution, what you said, is acceptable, Nakagami is acceptable, or some other generalized fading model will be more appropriate.
the first part is stochastic geometry model. It was first paper in 2010. There have been 10,000 paper on this. A lot of people actually validated it. Actually in all of the paper we publish, we always validate it with single results. We get data from either from city.
See, what I am asking is, if you really look for, say, device to device kind of communication with the channel model? European Commission has, I think we really look for HitNet design kind of model actually which what is basically the impairment model, how do you characterize the accumulated impairment from other business dealt with. I think the companies which are making a product, they might be using some kind of a standardized model, because ultimately for such designs we have to do some standardized model, and that standardized models only are available or in the literature available. Verification from actual measurements, unless, for example,
so that has been done.
Actual
Measurement we have done. So we actually set up some system in Austin also. People have also done it. They validated it with the real building data also, real base station deployment also. And then of course there is some difference. They characterize it and show how much will be the exact performance will be different than that, right? Then second part was also that like recently we published a paper on co-location. There we get data from major operators and we combine them together to prove that whatever we're proposing is actually matching very much to it, right? Then this Nagame distribution, those field trials were done by Rappaport group, right? And they showed that distribution is something similar to it.
I think they have done huge measurements, huge modeling. So basically, whatever you are doing, if there is some kind of a comparison, then
so,
you have been
so whenever we start, we always look at first at the data, like people have published, like when.
That's fine. But if you naturally throw your things to the audience, they naturally license with that kind of a thing. So that they can adopt. For instance, tomorrow I can adopt your thing. When I naturally want to go for D2D communication measurements, I go for analysis. But I have to be first convinced that your model is something that I can apply to my work.
Yes, sure.
So that is the thing actually we want.
I did not know what audience.
Slides where you can validate your model, some measurements.
So I assume people are coming from an analysis of this thing. They have read the content, so they of course know.
I have just eliminated one mind.
No, I understand that, but this question I always get in all the conferences.
Right.
And this we have been done from past 10 years.
Fine.
We have the hundreds of people on validation.
Fine.
So it's not easy to cover validation results from the starting. So we always say that we are using this and we can refer you to do, but it's always nowadays, like suppose it happened in past also, right? You once you come up with a new area, you do a lot of validation into it, right? But once you get accepted to it, you do not publish results or you do not validate it in each and every single paper. So this happens, this has been widely accepted.
I know when you consider the blockage, that can always be there in a small cell concept, suppose in a headnet.
So blockage,
you can have blockage.
so 3GP model also considers the same thing.
My early knowledge says that 20 years back knowledge I know that this is log normal. When I was waiting with the log normal distribution. You have a offline things. Right now.
Okay, log-normal distribution again is not good for it because it doesn't have distance-based criteria into it. It just fixed, but when you talk about urban settings, it's very careful. You have to see the distance of the serving link, because if link is very close, then line of sight based interference sudden will be 0. Okay, sure. This I mainly target about how we can apply tools rather than justifying it. Okay. For example, I have less time, so I'll just switch fast for this, and to switch fast track. So people have computed it, and this is the very first paper on millimeter waves using stochastic geometry in 2014, and there we compared to Austin and LA data, and we saw that blockage, like Austin has less blockage and LA has more blockage. Okay. But in that case, Austin will get high interference and LA will have small interference. So blockage actually helps in some case. But interference from noise is actually high. So you can see that noise I mean not high, if you go for 250 meters, 200 meters, interference is very small. Okay, so mainly you are still dominated by noise at least in the early deployments cases. Okay. Again, if you use a better antenna, the coverage can improve by a huge number. So 20 dB main lobe minus 10 dB side lobe, 30 degree angle, which is actually very nominal for millimeter wave. We're looking at even for 5 or 7 degree beam width. So it will be mainly noise limited, at least in the starting cases. And then this paper actually talk also about when I compare with a microwave performance, this is or millimeter wave with different base station distance. We found that you can actually get a very good, so this rate coverage is almost not decreasing, at least in this range, while the microwave rate coverage decreases very fast. Okay. So I have one more slide to cover, so I will not discuss much into this. So part 4, which was what we can guess. Again, this is clear that if you want to exact result, you have to do simulations. Right? There is no way around it. But we want to get some insights, right, for how to deploy things. Like we saw that if I want to scale lambda, how I can scale R, those kind of questions, right? So, how much should we densify? That is a question. Normally, if you have single pathless model that some R to power minus alpha, the SIR is invariant to density, but the SIR increases when you increase lambda. But this is not the case when you talk about some system which has dual path loss, which means when you go below distance R, path loss is different, but the base station when it's outside R, the path loss is different. Okay, that is happening when you go for ultra densification. Base station can come to a region where it can have direct, very strong connection. Similarly with millimeter wave, right? When you come very close, you have direct line of sight connection. So your alpha changes. In that case, once you do so much, first it helps because your serving base station become more and more line of sight. But once you densify more, interference star also become line of sight, right? And there is a result that if alpha interference from the line of sight base station is actually infinite. Okay. So we do not want that condition. That is why you will see as SINR lambda increases, your SINR can actually go to 0, right? The increasing lambda. So what is the good density? There should be some reason, and that is based on the blockage density also. So we found for LA 43 meter is the critical density. For Austin is 85 meters. Again depends on the blockage density. So blocking helps. Blocking makes it noise limited. Antenna elements also makes it noise limited because it reduces the interference. But density makes it interference limited. Which way should we go? So the answer is kind of initial deployment will always be noise limited. But once we have more and more deployments, we will start having interference limited, right? So we need to design systems at least initially taking care of the noise limited scenarios. Okay. Again, initial access in millimeter will be very difficult. If you remove the antenna gain from it, right, you will see the link budget is not satisfied. You get very low coverage. So even in the initial discovery case, you have to use antenna gains, right? You have to use directional beams to discover different uses, right? This means you have to search in each space. Suppose your antenna beam is 5 degree, so you have to at least do 360 by 5, 72 beams to search the whole space, right? In LT, you can just do single beam and then you can discover. So it's very complicated. So there has been a lot of work also which talks about how we can reduce the complexity of this initial discovery. And that is where the LT can be helpful because you can put a LT overlay over it. It can also help you to provide a control channel or at least in the initial discovery of it. And the worst part, if the millimeter wave fails for some reason, for high blockage or something, LT can still provide basic coverage. So you can always offload to LT, and then when you are good, you can always offload to a millimeter wave to get better coverage for at least higher data rates. Okay. The last part is spectrum sharing. So again, we talked about that interference is so low, right? So can normally people have exclusive licenses where the spectrum is divided into multiple operators, right? Can we do the same thing here? That was the question. But if we want to share, right, then do we need a spectrum database? Means do we have to take care of conflicts, that at what time what person is transmitting, or we can just do some uncoordinated sharing, means every base station is transmitting, right? Or so basically this was the question in generally people asked about. So what we actually showed we did that if you compare, this is blue one is the single exclusive sharing, and the red one is the spectrum sharing. Okay, this is rate coverage, means the probability that rate is above this 100 Mbps is 0.6. Okay, so we see that if we just target high data rate here, our target audience is high data rate users, right? Then it's always good to share spectrum. Even in median rate, you get at least 25% gain, and at suppose this, you get a very significant gain of around 100% or something like that. Double rate you get, right? But you lose something in the low rate users, right? Because of course, both are transmitting together without any coordination. So the people who are at the cell edge will be affected hugely because the interference will be large. Okay. Now the question comes, who is our target audience? Millimeter wave is basically for high data rate. Okay. Just for phone calls and other things, you can always offload to LTE and do there, right? If you read a very high data rate, then you go for millimeter wave, right? So this may be a good strategy to actually share the spectrum, because that target high audience, rated audience, we get again. And when we care about the small one, we just offload to LTE. Okay. But this can be further improved if we do some kind of static coordination. So this sharing means you cannot connect to the other operator, but the whole spectrum you can use for transmission without any asking. That's the question. So both as 100 MHz, 100 MHz, there is 200 MHz bandwidth, you can use the other one fully. So each operator has its own base station density. One comes with about 30 base station, other comes with 30 base station. So that blue shows when they don't coordinate. They just like separate. But then they mix together and say, no, we want both, let's use both. Because of the key point is actually directionality here. See, this is beamwidth. If I have 60 degree, then spectrum sharing works. If you go, then spectrum sharing doesn't work. For LTE, beamwidth is generally, you use kind of 120 degree beams, right? For you have 3 sector deployment, each has a 120 degree beamwidth. There, you will be in big loss, even for the median rate, if you try to use spectrum sharing. Here the benefit is since the beams are so narrow, you get a good serving, but there is a less probability of having interference, right? So that is a key point here. If you do not have this beamwidth, you are not able to share spectrum. Okay. Again, this is for symmetric operators. For asymmetric operators, there is some game theoretical concept also comes into picture. Right? I haven't covered there. And static coordination is simply, I looked at a very simple one. You have different operators. So the secondary one looks at the primary users and try to see what primary users are around it. And it adjusts its power in a way that the interference at the closest primary is less than some threshold. Okay. So as you increase that threshold, this is the threshold, you get more and more, you get less restriction. You can transmit at high power, right? So less means you are not transmitting at all, and high threshold means you are transmitting totally, right? And when you compare with the rate I got with the uncoordinated one, there is some threshold where the total rate of the primary and the secondary can go up, right? And also the edge rate improves. So median rate also improves and edge rate also improves. This means you get an overall gain in the whole thing. Okay. So people have also looked at some more complicated cases of coordination spectrum sharing, but those are more, all are generally simulation-based approaches. Okay, but they have shown significantly that spectrum sharing is a viable option, right? This kind of result helps us to understand basically the key concept of is there a gain, is there a gap there or not, can we gain something or not? Okay. So one thing which I didn't cover is also this, see this green part. This green part shows is same as red one, but when the base stations are co-located. So this means at the same tower you have two base stations. Okay, all the base stations are like that. And that I said in earlier case, it increases the interference by a huge amount, because wherever your serving power is, you get the same amount of interference at the bottom also, right? Only thing is, due to directionality, even if the path loss is same, if the beam is pointed in some other direction, you will not get, you get a very low interference. One second, just let me finish. So that is why you are able to actually get a similar performance even when the case when two operators are sharing the infrastructure. So this is very important, because we expect that most operators will be actually sharing their base stations at the same location in this. Coordination many times doesn't depend on just the location. It's because if you're AT&T tower and you are Vodafone tower, you cannot just close, you cannot coordinate. There's a whole lot of security issue, administration issue, roaming issue, revenue issues where you want to coordinate, right? There should be a bigger deal from the top management for these things. No, you are not. I'm not allowing to connect to my base station. I don't have to care about security of it. I don't have to roam his data, right? I'm not doing roaming on his data. I'm just allowing my spectrum for him to use. And both are getting a very huge gain. So it's of course, there is of course some kind of MOU need to be signed, but it's very easy to do than actually doing a full base station sharing. You have to lay infrastructure to support other operator, you have to support their user discovery, cell discovery, everything like that. So just the transmission conflicts, right? Yeah, you can do that. That's why I said this static coordination which I talked about is not just primary, secondary. It can be for cellular operators also. If they are together, they can have some kind of thing that I am not overloading my system, but I can do some kind of small guess that if you can do dynamically sharing a spectrum at a particular location, something like that. Yes. So for that case true, but for infrastructure sharing it may not be true that you want to connect to other base station. That will be more complicated. Okay, so that's end. Yes. No. There's a tower. There's only side tower there. Base stations are still different. It's like there's cases when there is a bridge, and government only made one location where you can put base stations. You cannot have more base station in the bridge, right? So you have to put your base station in the same tower, but the base station will be separate for each one. Co-location means the location is same, not the base stations are not same. Yes. So location means you need tower requirement, you need safety, security there, right? You need shade there. So that some other person comes and say, I own this rental space. I'll put a power generator there, I'll put a shade there, everything security, everything there. You just put base station here, something like that. And then if you don't want, you can just move out any day you want. So that is a good point instead of buying the land.
That brings us to the end of the first tutorial session for the day. I'd like to, convey our heartfelt thanks to Dr. Gupta, and we also have a small token of gratitude from IIT-Hyderabad to Dr. Gupta. So a couple of things. So we'll now break for lunch. Lunch is at the upper dining hall. A bus service has been arranged for you to go. from here to the dining